Okay, so we have 107 students, 106. So 35 plus ni. Okay, so this is the third lecture. Um, we will meet tomorrow for a tutorial session. Um, and the tutorial will be based on today punya lecture lah. So our assessment will start this week. So hopefully all of you have finalized your add and drop courses. Okay. So today we will continue. This is the ingredient for this course, the main topic. The first two topics. The first topic just introduce you about the information retrieval, and then the second topic give you an overview about what is the user interface for information retrieval and what kind of research that they are doing. Okay, for this lecture, this is the third lecture, we will discuss about the classic model on how do we model information retrieval. Okay, how do we model the data, and then later on we use the framework in order to retrieve the inf information or document that are requested. Okay, so the session for today, we will look into some of the introduction about IR model, the basic concept, and also we look into the first model. We call it the Boolean model, and then we move on to term weighting, and then after that we improve the term weighting by introducing the vector model that will use the probabilistic model. So these are some of the classic models that are used for modeling text structure, okay, text document, and then later on we use this framework or environment in order to retrieve document. Okay? So if you have any question, you can stop me. Okay. So modeling in IR or information retrieval is a complex process. The basic idea is we want to be able to perform ranking because when we type in the query, we want to have the capability to retrieve the document based on the relevancy of the document with respect to the query. And at the same time, we want to be able to rank that document. Okay, so the ranking function that we're talking about is a function that assign some score to the document with regard to a given query. So given a query, the system should be able to rank the document based on the degree of relevancy of the document with respect to the query. Okay, so this process consists two main tasks. The first one is we need to be able to represent the document so that the system or the program knows what is the content of the document. Okay, so for us, for human being, we will be able to interpret or we will be able to perceive what is the content of the document. But how do you make the system knows that the content of this document is such as such and so on? Okay, so we should be able to create a logical framework in order to represent this document so that the system knows that, okay, I have this query. How do I compare with the document that I have in my storage? Okay, so we need to have this conception of a logical framework for representing document and query. Okay, so once we have that logical framework, then we will be able to compare. We'll be able to quantify the similarity among document and queries. Okay, and this is very important because um, if we do not have the logical framework, how do you quantify the differences or similarities between document and query? So very hard for us to quantify the document and also the query that we want to look for, and this will not give us a consistent output. So by having this logical framework, and then we use the ranking function that we define, we can quantify the similarities among the document and the queries. So these two are the most important part. First, we need to learn how to um, represent the document. So we need to have a framework, a logical framework to represent this document. After that, we learn how to quantify, how to differentiate the document and the query that we have. How do we find similarities? How do we find the differences? Okay. So you will be learning this too, mainly throughout these courses, looking at the model and looking at the ranking function. Okay. So IR system usually adopt index term or keyword that they have in the document. So it is easier to use the keyword that carry some concept, or usually they take the nouns like the person, things, place, and idea to be the main index in order to tag the document. Okay, so in a more general form, it is any word that appear in a document that carry meaning. Okay, so we do not want to have something, some word that carry no meaning, and then we use that word to be one of the index term. Okay, so we want to have as small as possible all the index term that can be used to represent the document. Okay, um, it also says that, let me take my pen. Where is my pen? Okay. It is also said that the retrieval based on index term can be implemented efficiently since index term are simple to refer to in a query, because the query that we type are all the keyword that um, similar to what we have in the document. So we want simplicity. We want to have a simple retrieving system that use index, which is both can be extract from the document and also from the query. Okay, so if we have this term or index, or sometimes they call it keyword, in both query and also in document, so it is easier for us to compare the similarity between the keyword and the um, document. Okay. Okay. The second part, like I mentioned just now, we should be able to have a ranking function. We need to define a ranking function that when we retrieve the document, so this is your query, and then this is the document that you have in your database. So we want to match the term that we have. So there must be intersection of terms, and then based on this intersection of terms, we can retrieve the document and then we can rank them. Okay? So when you normally type in a Google, we always expect that all the relevant document are displayed on the first page, and then when we go to the second page, they are more or less like less important with respect to your query. Okay, so a ranking is an ordering of document that reflects their relevance to a user query. Okay? So we expect that when the document are retrieved, they are displayed in according to the degree of relevancy. So the top one, the most important one, and then the least important will be displayed at the bottom. So this is based on some kind of ranking function. So you will learn later on how to compute the distance between the query and also the document. Okay, if the distance is very small, that means they are more similar. Okay, okay. So the IR system deal with the problem predicting the relevancy of the document, and this problem naturally embodies the degree of uncertainty and vagueness. Okay, so remember last time in lecture one, we compare about the um, data retrieval using SQL and also the information retrieval using this technique. In database, we are looking at exact matching. Okay, but in information retrieval, we are looking at the degree of relevancy. How much, what is the degree of relevancy of the document with respect to the query? Okay, so we are dealing with the degree of uncertainty, okay, not exact matching, or sometimes we call it vagueness. Okay, okay, so this is the model, the standard model that we have. So we will have a quadruple in which we have the first one is the document. This is a set of logical view for the document in the collection. So D refer to a set of collection. And also we have the query. Okay? So a query is a set of logical view for the user query. Okay? So we will have a vector of document and a vector of query. And we also have this ranking function. Okay, so the ranking function is defined as a function that will quantify the similarity between the document and also the query. Okay, so the ranking function is used to quantify the differences between the document and the query. Okay, and the whole thing is what we call the framework. Okay, so this is your framework. So this is the framework that we will be dealing with in this course. So we will have the document, we will have the query, and we have a ranking function that is able to quantify the differences between the document and also the query. Okay. Okay, this is the taxonomy of IR model. In this course, we are dealing with text document only. Okay, so text document only will bring us to here. Of course, there are some other type of information like links and multimedia. So we are looking at text only. So we will looking at the classic IR model. Okay, so Boolean, vector, probabilistic, and then we will look into some of these. Okay, so we will study more on this area, and then the application. We will look into some of the technique that we can use in order um, to perform text classification or uh, text topic modeling and many more. Okay, so we will focus on text document property. Okay, and we also look at the type of res result that being displayed. The first one is called ad hoc. Ad hoc means um, you will put in the query and then they will provide the document based on your query. Okay, but there is another one. This is based on your profile, they call it filtering. So they will return a document that is considered relevant to your profile. Okay. So if you type in your query, you will be getting different um, document depending on your profile. So this is what we call the filtering. Okay. Okay. This is some of the basic concept before we proceed. Um, in each document, they will be represented by a keyword or index terms. So index term is a word or group of consecutive word in a document. So it could be one word or more than two words. Okay, so phrases of word. Okay, a pre-selected set of index term can be used to summarize the document content. So which means that if you have one document, you will not use all the terms that exist in that document. You will be very selective in finding which are the index term that um, most important that can be used to summarize the document. Okay, so you don't want to have long list of vocabulary for your information retrieval. So you want to reduce the number of vocabulary. So what you do, you just select the um, most important one only. And however, it might be interesting to assume that all words are in index term. So meaning that how large is your vocabulary that you can fit into the system. Okay, so if you look at your dictionary, some of the term no, some of the stop words are not there. So, for example, stop words like this, they are called stop words because they do not carry any meaning. Okay, so for example, is the he she and so on. So if I look at this page, this is not a good index that can be used. So this one can be removed. Okay, so this is all the stop word. Okay, so I can use all of this to represent this page, but I will remove all the stop word. Okay, so this is to reduce the number of terms that I can use to index the document. Okay, so when we talk about the vocabulary, um, there is a limited space because we want to have a fast computation when we want to compare. So we want to limit the number of vocabulary that we have. So we will say, okay, in the vocabulary, we may have up to T keyword. Okay, so we have 1, 2, 3, 4 up to T. So the size of our vocabulary will be T. Okay, so the size of our vocabulary is T. Okay, so when we want to create this vocabulary, we want um, to limit the number of keyword. We only keep the one that is most most important. Okay, that carry more information. Okay, so later on we will look into what are the terms that are more important compared to the other word that is less important. Okay, so since we are looking at the occurrence of the word, we can use the binary representation to indicate the occurrence of certain word. So, for example, if we have vocabulary up to T, okay, up to T, then we can use the binary representation in order to indicate the occurrence of the keyword in the document. Okay, so in this case, for example, okay, let me give you one example. For example, if we only have three or two keyword only, so you will have this pattern in your um, let me erase this too big. Okay, let's suppose I have keyword 1 and keyword 2 only. Okay, so I could have this pattern. Okay, so this one means that both keyword 1 and keyword 2 does not exist in the document. This one keyword 2 exists in that document, keyword 1 exists, and both keyword 1 and keyword 2 exist. Okay, so in this example we have t keyword, so we have this number of pattern. Okay, so for example, this one we have 2, so we have 2 to the power of 2, so we have 4 number of patterns. Okay, so each of these pattern of term co-occurrence is called term conjunctive component. Conjunctive component meaning that um, you combine them using and. Okay, so that means uh, for this one 0 and 0, 0 and 1, 0, 1 and 0, 1 and 1. Okay, so term conjunctive component is that we are combining them using the and. Okay, so we will use this term, the conjunctive component of that document. Okay, okay. So for example, like this, if this is your document, so the conjunctive component of your D1 will be K1 and not. Okay, so all of this not because the value is 0. Okay, so the expression must be true. So that's why you put this one not because this is 0. And compared to the dn, you will have k1 and k2 and k3 up to kt. Okay, so this is how we use the Boolean model in order to represent a single document in your storage. So we use the and this is called term conjunctive component. Okay, any question so far? If you okay, can you type number 1? Okay, ikut saja nih. Macam lebih kurang 50 lah yang pay attention. Why k t minus 1? Yeah, because we have we have up to t number of keyword. So what is the previous number? So it should be kt minus 1 lah. And the next one here will be kt minus 2. Because this is just in general only. Because t is the number of the size, the number of keyword. So t could be any number. So if we have 6, so the previous one should be 5 lah. 6 minus 1. Okay. Any question? Okay, so please tomorrow we will have the tutorial, so make sure you understand this one. Tomorrow, by the end of the session, you need to submit. So please bring your own paper for submission. Okay. So any question? No, that's good. You asking question. Okay. So now we will have this, what we call it, the term document metrics. So um, we use the term document metrics in order to show the frequency of the keyword that exists in the document. So if we have this F here, so this is the frequency of keyword 1 in document 1. So this one is referring to the frequency of keyword 3 in document 2. Okay? So this is what we call the term document metrics that um, display the occurrence of term K, I in a document J. Okay, so we will use this one to represent the document, and then at the same time we know which keyword exists in the document and how many times they exist. Okay, so we will use this term document metrics. Okay, so the logical view of a document, because our aim is to have this vocabulary. Okay, so since I mentioned just now, we are looking at all those important words only, so we do not want to have stop words. Okay, so these are all the phases or pre-processing step that we need to do. So the first thing that we need to do is, when we receive the document, we have to know what is the structure. Okay, so remember in the um, second lecture, we are looking at the structure of the document. We know that the topic, we know the section, we know the author, and so on. So we need to be able to extract the content. Okay? And then we look at the remove some of the blank space, funny character, all the numbers, and then we remove the stop word. Okay, so remember stop word is like she and so on. We collect all the noun group, okay, the nouns, and we also perform stemming. Stemming is a process of finding the root of the wood, okay, the the stem of the wood. For example, play, place, playing, and then play. So all come from play. Okay, so we will remove all these things and we say, okay, play. The word play exists 3 times, but in the form of plays, playing, and played. Okay? So that is the um, process involved in stemming. We are finding the root of the word or the stem of the word, and then we will just keep that one only. And then once we have finalized all the vocabulary, then we will put them in here. Okay? So once we get the taxonomy of keyword, then we will have all the term 1 here up to term X here, and then this is your document. So this is term document matrix. Okay. Okay. Any question? Any question? No. If you're okay, can you type number 2? Okay. Okay. So the first part is just the introduction. So now we are looking at, okay, how do you use the model that we have now in order to retrieve the document? Okay. So tomorrow in the tutorial session, when we meet face to face, you will be able to ask me how to do this, how to do that. But before you ask me, you need to know the basic knowledge on how to apply the model. Okay. Um, I will guide you on how to solve the problem, but you need to solve the problem on your own. Okay. So we have a few models here. The first one is called Boolean, and then the second one is the um, weighted term, and then the last one is vector space. Okay. So we will look at the Boolean model. So the Boolean model now is based on the basic model that we learned before, where we use binary. Okay. Okay. In the Boolean model, we just use the expression. So the expression that we have now is in the form of binary expression, in which we use this is n, okay, and this is o, and this is not. Okay. So I believe you have taken what, logic. Okay. So you learn all the binary number. So given we have a query that consists keyword A, B, C, but the way we read this one is that, okay, given a query that consists keyword A and keyword B or not keyword C. Okay, so which means that we give priority for this one first. So either the document has keyword B or not keyword C. Okay. So for the expression to be true, both left and right expression must be true. Okay. So since this is a Boolean model, we just use 0 and 1 only. 0 if they are not in, then the document does not contain. 1 if the document contain the keyword. Okay. Okay. Now we move on to this one. So we know that um, the query conjunctive component will be like this. Okay, they are expressed using and, or, and not. So this is your and, this is your not. No, this is your and, or, and not. Okay, so this is not. So this is in the form of query conjunctive component. Okay, conjunctive meaning that the whole expression must be true in order to have the query to be true. And this is what we call the disjunctive normal form. Disjunctive normal form use the O here, but they express the value that will be true for your query here. So meaning that um, a query Q can be rewritten as a disjunction of those components. So meaning that if I plug in the value 111 inside this, I will still get my query to be true. So since we could have many possibilities of combination of binary. So I found that uh, these three, these three, let me use different color. Okay, so this is one, this is two, and this is three. All this value, when I plug into this expression, my query will be true. Okay. So for instance, if I use the last one, here, I put 100. Okay. So this term will become 1. Okay. And the whole thing will become 1 because I'm using O. And then true and true, I will get true. Okay. So the disjunctive normal form will list all the possible pattern or combination of binary that will make the expression for your query to be true. So meaning that all the document that has this pattern will be retrieved. So 3 document will be retrieved because we have 3. Okay. Any question? Maybe you have question here now. Okay. Any question? Okay. Izudin has raised a hand. Yes, you may proceed to ask me.
Ada
Yeah.
yang QDNF yang equals to 111 or ke N patutnya.
Ni or. Okay.
Oh, bukannya
So
kau yang atas ke?
yang ini disjunct normal form. So disjunct will combine all the possible combination, meaning that I will have the first one, the first value, or this one, or this one. But for the conjunctive one, the conjunctive is this one. Okay, they are combined using the and here.
Oh, okay.
Okay, so this part is considered as one part, and the second part is this one. They are in bracket. Okay, like we go back to here. Okay, so this is in conjunctive component. Everything will be combined using the and, all and kan? Okay, but this one can also be rewritten as disjunctive, but this one using this all. And the reason why, because for this one to become true, we could have many possibility of binary pattern. So for example, 111 or 110 or 100 can give or can provide your query to become true. Okay. So conjunctive, they combine the expression using and. Disjunctive, they combine all the expression, the value of the using or. The value of the all the keyword, they combine using or. Okay. Boleh? Okay. So if you look at the diagram here, this is the location where the keyword can be found. Okay, so one means they are in the keyword A, and then this one means keyword they are outside keyword B and outside keyword C, and then the middle one here is the keyword A, B, C. Okay, so with this expression, the blue one is your area of retrieval. So you cannot have all the document in here or here will be retrieved. You only retrieve document that falls in the blue one. Okay, uh, let's expand the vocabulary to four. Okay, so your keyword now you have B, A, B, C. Okay, and but you look at your query just now. Yeah, you look at your query here. Okay, now we have four keywords, but your query only consists of A, B, C. So meaning that you don't care whether keyword D exists or not. Okay, you don't care because all you know is that okay, I only need to know that the document must have this expression. Okay, so this expression is this one, and this one, and this one. Okay, this expression is the same thing as we have before. So this is the expression that we have. So so remember this 3 1. Remember this. Okay, so we could have this. If we plug in here, the expression will be true. If I plug in 110, the expression will be true. Okay. So if I put 1100, expression will be true. Okay. So now we have keyword D, the fourth keyword, but our expression only consists of A, B, C. So meaning that I don't care whether keyword D exists or not. So for that reason, my disjunctive normal form will become more because in here I will list this both. So 3 1s and then 0 and 1. So meaning that I will include one, but I don't care about this, the last one. I will include all the 110 and I don't care about this. So I will include 0 1 because only two possibilities. Okay. So I will include the pattern 100, but I don't care about this. Okay. So meaning that if we have this, um, the query that I have is that okay, I just focus on A, B, C, and I don't care about KD. So meaning that um, I will take 1 and then I don't care 0 will be true, and then 1 also will also be true because these two I don't care. So, but I need to include because both 1 will be true also. Okay. Okay. So the similarity of the document DJ to the query is defined as follows. Okay. So if, for example, the document match one of these, contohnya that document consists of this. The document one consists of keyword A and keyword D. Okay. So the pattern for this one is 1001, kan? So which is this one? Okay. So if this is 1 and the rest is 0, the value for the disjunctive normal form will be 1. So meaning that this is the document that will be retrieved with respect to this query. Okay. So if you look at the type of result returned to you is only the document, and the similarity between the query and the document is 1. Okay. So over here, we will return the document and the similarity value will be 1. Um, if if there exists a conjunctive query such that the conjunctive query is equal to the conjunctive document J, okay, and 0 otherwise. Okay, so the Boolean model predicts that each document is either relevant or not relevant, 1 or 0, true or false only. Okay, okay. So the retrieval based on binary decision criteria with no notion of partial matching, meaning that you cannot do ranking. So the Boolean model only retrieve document that is equivalent to the query, that is considered equivalent to the query. So you cannot perform ranking. Okay? So the information need has to be translated into Boolean expression, which most user find awkward, meaning that at the end of the expression, you only can get true and false, 1 or 0. 1 if they are the same, 0 if they are not the same. Okay, so this is too simple, and they say that we cannot use this because this model cannot do document ranking. Okay, so the model frequently return either too few or too many document in response to a user query. Okay, so any question? If you okay, can I type number 3? How many of you still paying attention? Okay, kurang 50 nih. Okay, okay. Next, due to the reason that for Boolean model we cannot perform ranking, so they have introduced a new model that consider term weighting. But before that, we will look into this term weighting. What does it means by term weighting and how they use the weighting to rank the document? Okay. So in the Boolean model, we only look at the occurrence of the term in the document. But the term weighting here, they refer to the frequency of the occurrence, how many times the term exists in the document. So the term of a document are not equally useful for describing the document content. So for this one, we look at the word which appear in all document or part of the document. Okay, so usually a word that appear in all document is completely useless. Why? Because if a word is always exists in all of the document, we cannot use the word to differentiate the document. Okay, for example, in all of the document we have this word is. So we cannot use is to be the index term to differentiate the document because all the document has this word. Okay, so that's why it's very important for us to find index term which is unique and not all document consist that term. So in the term weighting, we are looking at the frequency uh, as the weightage of the wood. So if we have 0, meaning that they exist 0 time. If they are 5, meaning that they exist 5 times in the document. Okay, so the weight here quantify the importance of the index term K1 for describing the content of DJ. Okay, so this is the document and this is the keyword. Okay, so this would are useful to compute the ranking. Later on, we will look into how do we use the number. Okay, so we will then have a list of keyword K1 up to KT, and each of these keyword will have a weightage for that particular document. Okay, so this one we will look into the frequency of that word in that document, the frequency of keyword 1 in document J. Okay, so we can define the document as a vector, word 1, word 2, and up to word T. So we have T number of vocabulary index term. Okay, T index term in your vocabulary. Okay. Okay, for the weight that we use here will be the frequency. The frequency will be used um, to be the benchmarking used to um, represent the index term. So, for example, like this, um, let Fij, so meaning that the frequency of keyword I in document J. Okay, Fij refer to the frequency of keyword 1 in document J. Okay, so the total frequency of occurrence, capital letter I of term Ki in the collection is defined as all the frequency of I in all of the document from 1 to n. Okay, let me give you one example here. Okay, so in the first one, we say that the frequency for do in D1 is 2. So meaning that we look at in document 1 and then we find how many do. 1, 2. So that means the frequency of do is 2. Okay. If you look at the do in document 4, in document 4 we have 1, 2, 3, 3. Okay. So we have 3 times the word do exists in document 4. Okay. So since we have all the document 1 to 4, so if you have the capital letter F do, so that means we just total up all this value. Okay, and we have 8. And N here referring to the number of document that consists do. So we have document 1, document 3, and document 4. So we have 3 documents. Okay. So this is how we quantify the word in each of the document using the frequency. We use frequency of the term occurrence. Okay. Okay. Um, when we have this, I need to go back here. Okay. Can you see the slide? Okay. When we have this term document matrix, we notice that for all of these keyword that we have, this is a single term. Okay, a single term. But sometimes we have software engineering or computer science. These are the words that always come together. Okay, so if we represent them using the term document matrix, so we have lost the sequence of the word. Okay, we no longer have the information about computer science. We only have keyword 1 as computer and keyword 2 as science. So we do not have information how many times keyword 1, no, um, how many times computer science exists. 2 terms. Okay, so for that reason, we have this what we call term-term correlation. So the term-term correlation will find two terms that always come together in the same document. Okay, so for example, the term computer and network tend to appear together in a document about computer network. We also have software engineering, computer science, and so on. Okay, so how do we capture this? How do we compute or how do we find two terms that always come together in a document? So we use the term-term correlation matrix. Okay, in the term-term correlation matrix, what we have is that we make use of the term document matrix that we have. Okay, so in here, this is your basic formula. Okay, so we take the transpose of this matrix, so meaning that the row column will become column row. Okay, so I will transpose this matrix, so the document will become the row and the keyword will become the column here. Okay, so once I get this, then I take the multiplication of these two matrix to get this matrix. So this matrix will tell you how close they are. The higher is the value, the more close they are. Okay, so how do I calculate this? So I take this row and I multiply with this. So meaning that I multiply this plus I multiply this. Okay, so this is what you get here. The second round, you will take, let me change the color. I take this and then I multiply with my second one. Okay, so this is how you get this one. And the last one, I will take the same thing also, but I multiply with the third one here. And that's how I get this one. Okay, so so this is considered as one value. Okay, so I will repeat again this one with this, so I will get this one and so on. So by the end of the calculation, we have this value or this matrix. So this matrix will tell you the correlation between keyword 1 and 2, keyword 1 and 3, and so on. Okay, so the higher is the value we get here, the more correlated they are. Okay, okay. For example, like this one. This one is the keyword, and this is the document. And then I transpose this to become transpose of that matrix, and then I multiply them. So this one multiply with this. Um, for that one, I don't have to do because this is K1 and K1. And let's do the second part. Okay, so I multiply that one. So this is what you get here. Okay, 1 times 0 plus 0 times 1. And then I do it again for this and this one. So that one will be here. Okay, so 1 times 1 plus 0 times 1, you get this. Okay. So you do it for the rest of them, and then you you add up the value here. Okay, so based on this matrix, we can say that the highest number here is this one. We can say that keyword 3 and 4, they are the most highly correlated term. Okay, so this is how we capture the occurrence of two terms that always come together in the same document. So we don't have to worry about losing the information, because when we transform the document into term document matrix, we only consider one single term per row. But we can capture again the term-term correlation by using this term-term correlation matrix. Okay, so don't worry, you will have your assignment on this to make sure that you do a little bit of thinking on how to solve this problem. Okay, any question? If you okay, can you type number 4 now? Do you have any question? 3, 3, 4, 3. Yeah. Okay. Doctor, can it differentiate between computer science and computer science? Yes, because in the pre-processing later on, you will see that all the capital letter will be converted into small letter. So that one we will do some pre-processing. Okay. So yang huruf besar tu semua will be converted into small. So you don't have to worry about that. So that is part of the pre-processing. Okay. Any other question? No? Okay. So we proceed with the next one. Okay. Okay. So for this one, for the previous one, the term weighting, we are looking at the frequency of the term. Okay. But in the beginning, let me. Okay. Um, look careful for this one. This one. It says that, for instance, a word which appears in all documents of collection is completely useless for retrieval tasks. So meaning that if you have one word that exists in all of the document, we cannot use that word to differentiate them, right? Because they appear in all documents. So how can we use that word in order to differentiate the document? So there is a way to solve this problem. How do we not count that word to be part of the calculation? Okay, so we need to introduce the TF-IDF, term frequency inverse document frequency. Okay, so this one stands for term frequency inverse document frequency. This is the way that we are looking at, and we will not count the word that always exists in all the document. So we make their weight to be 0. Okay. Okay. Let's start with the first one, TF, term frequency. So the term frequency here referring to the occurrence of the frequency of occurrence of the term. Okay. So basically, we're just looking at the frequency. The frequency of keyword I in document J. Okay, the frequency of keyword I in document J. Okay, So that is TFIJ, term frequency for keyword I in the document J. Okay. Okay. There is a variant of the TF here. Over here, we are looking at the frequency. Okay. And one of the variant is this one, in which we use the log 2. Okay, so for example, for all the frequency of keyword I for document J, which is greater than 0 or more, so we will compute using this. So meaning that if your frequency Fi, if your frequency of if your keyword I frequency is 2, so your value will be log plus 2, 2 here. Okay, so this one will turn out to be 2. Okay, so they simplify this one using the log 2. Okay, so the log expression is the preferred form because it makes them directly comparable to IDF weight. So later on we will discuss that one. Okay, so from here, from this formula, now we are using this formula. Basically, they are the same. So the reason why we use that one because we want to match with the IDF weight later on. Because later on we will look into what is TF-IDF. Huh? Okay. Okay, let's take a look at how do we convert the term frequency to be the new value. For example, like this, like the 2 here. Okay, 2 in document 1. How many times that exists? 1 and 2 and 3 and 4. So 4 times. Okay. So the formula that we have is the new one. So this is 4. Okay. So when we solve this one, we have 3. And the weight is 3 here for 2. Okay. So similar for the do in document 3. Document 3, we have this. The do is how many times? 1, 2, 3. So 3 times. So we have 3 here, and we solve this one, we get 2.58. Okay, so 2.58 lah. Okay, so first, to make it easier, the first thing that you need to do is you create a table of term frequency yang normal tu lah. Then you convert them using the new formula here that use log 2. Okay, and then you get this table. Okay, understand? So this is the weight that we have for each of the each of the term in the vocabulary for all the document that we have. Okay, but notice that here, you look at this value here. So meaning that B exists in all of the document. Okay, so our goal is we want to put the weight to be 0 because we do not want to have the word B to have an influence on the final calculation. So we want to slash out these two. Okay, so how do we slash these two? So we use the inverse document frequency. Okay, so what is the formula for inverse document frequency? Okay, so for the inverse document frequency, we look at the specificity, which is a property of the term semantic. It says that the more the word exists in the document, the less important they are. Okay, so the inverse of the number of the so when we look at the term specificity, term specificity should be interpreted as a statistical rather than semantic property of the term. So when we look at the frequency of the term in the document, we are not looking at the semantic, but we are looking at the statistical aspect of the term, which means that if they exist in all of the document, we cannot use that word to differentiate all the document. So for that reason, we need to remove them. Okay. So the formula for the inverse document frequency will be this. So where this one is referring to the number of document that consists that keyword I. Okay. And this and I referring to number of document that consists keyword I. Okay. So when we say inverse document frequency for keyword I is equivalent to log 2 n, where n is the number of document you have, and this is the number of document that consists keyword I. Okay, so let's assume that keyword I exists in all document. So what is ni, which is n? So when we solve this log n and n, so this is 0. Okay, so we will use the IDF to make the weightage of the word to be smaller if they exist more times, and then the weightage of the word to become higher or bigger if they occur least time number in the document. Okay, let's have a look. How do we compute this one? So for example, like this, 2. Okay, 2 exists in document 1 and 2. Okay, so that's why we have here. Okay, so to calculate that one, we have how many document? We have 4, and then this is 2. So this one is equivalent to 1. Okay. Look at this B. This B exists in all 4 documents. So the IDF will be 0. Okay. So how do we get 0? Because log 4 divided by 4 based on this formula. Okay. So we compute all the IDF for each of the word, and then we multiply with the previous table that we have just now. Okay. So this is your TF times IDF. Okay, so this is your new weightage here. So in this formula, we are using the IDF to cancel out the weightage of the word that exists in all of the document. Okay, so for example, like this is your TF. Okay, and then this is your IDF. So to get the IDF, no TF IDF, we have to times all this with all this. Okay, 2 times, no, not that one, this one. Okay, so 3 times 1, you get 3, and then 2 times 0.415, you get 0.83, and then 2 times 2, you get 4, and then 2 times 0, you get 0. Okay, and you do it again for this 1, 2, 3, 4, 5, 6, 7. You multiply with this 1, 2, 3, 4, 5, 6, 7. Then you get this. Okay, so this is your TF-IDF. So this is the document representation that you will be using to perform the ranking later on. Okay, so this is what you should be producing at the end of the trying to construct the TF-IDF matrix. First, you find the term frequency. and then you find the IDF, then you multiply them to get this table. And this is your table that you will use in the next chapter. Okay, any question? Okay, so but we also have to look at the length of the document. Okay, in this example, we have all document to have the same length. Okay, the same length. But in some cases, we have document that is longer compared to the other document. Okay, so we need to normalize the document. So we can normalize them using the document length. So the document length can be computed using the size of the bytes or the number of words or the vector norms. Okay, using the vector norms, we are looking at here. So this is the document length. So basically, each document here can be represented as the weightage for individual keyword that we have. Okay, so in order to look at the length of the document, so we just square this value plus square this value. So basically, we just take the square of all of this, and then we sum all of them and then take the square root. So this is the length of the document. So the length of the document will be used later on to normalize your weightage later on. Okay. So how do we use that one? Um, so this is the value that we have for each of the document that we have for this. Okay. So how do we get this one? For example, so we have document one. So the content of document one is this, 3 only. So basically we have 3 and then 0.83 and then 4. Okay. So the length of document 1 will be the square root of 9 plus 0.83 square plus 16. So if you solve that one, what is the answer for that? Square root of 8.3 times 8.3 plus 25. So you get 25.6. So square root of this. So you get 5.068. So this value will be this one. Okay. So this one is basically the document 2. So which has the content of all of this. 2, how many times? 1, 2, 3, 4, 5, 6. So 6. So basically you have 2, 2, 2, 2, 2, and 2. And then the length will be square root of 2 this times 6. So which is 4 times 6, you get 24. So square root of 24. Square root of 24, you get 4.89. Okay, this one. So that's how you use this document, this formula to compute the document length. Okay. Okay. Any question? Okay. Any question? No. Okay. So the next one is vector model, but this one I think, yeah, a little bit more. Okay, let me finish this one lah. Okay. So the last part of this lecture is about the vector model. So this is used to represent the document, and at the same time we will find the distance between the query and the document. Okay. So what we are looking at here is the degree of similarity, and based on that degree of similarity, we are trying to find the ranking of the document. Okay. So based on this representation, we are looking at that each document is represented by a vector. Okay. So if we look at here, the vector of the document dj. Okay. So each document will be presented as a vector. Okay. The same thing goes to the query. So if we have the document over here and the query is over here, we can somehow compute the degree of differences here, which is this one. So we will be using the cosine function. Okay. So if they are close enough, the value for this one will be 0. And so your 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 document and then your query, you want to be closer, so that the closer they are, your value for the cosine function will be 0. Okay, so we can use the cosine function to compute the similarity. Okay, so what we do is just we take the um, product of the two vector, divide by the magnitude of each vector, and times the magnitude of document J and then the magnitude of the query. Okay, so how do we use this formula? Okay, so the weightage for the keyword I in Q will be using the same formula. Okay, and this one refer to the frequency of keyword I in the Q, and these two are the same. So basically we are looking at the same formula here. Okay, so finding the weightage is the same for the query. Okay, so for example, if your query is this one, to do, okay, so this is the weightage for 2, and this is the weightage for do. Okay, so the IDF we get from the previous calculation. So for the 2 is 1, and for the do is 4.415. Okay, and this is the frequency of 2 in Q, which is one time. This is the frequency of do in the Q one time. Okay, so if we complete this calculation, we have this. So this is the vector for the Q, and this is the vector for the document I. Okay, so now we have these two vector. Now I want to find how similar they are. So I will use the cosine function. The cosine function, okay. So I have the Q here, I have the D1 here. So how do I get this one? So basically I times 1 minus 1 times 3 plus this times this plus this. So notice that we have this 1 times 3 and then 0.415 times 0.83. And we don't have to compute this because this is 0. Okay? And this is the length of document 1. Okay? Based on the formula here, you take the document times the query. But in this one, we do not have to take times because for all of this formula, let me erase. For all of this formula, we have the same Q, so we don't have to add that calculation just to simplify them. So this is times the query, okay, times query times query. Up, yeah. So since all these Q are the same, I can remove them just to simplify my calculation. Okay. So, but this all in each of these calculation, the document length will be different depending on the number that we have here. Okay. So that's how we get this. Okay. So based on the result, this is the best value. Okay. Okay. What is the value for this? Can you find? What is the cosine 0? If you can find the answer, we can go home. What is that value? Cosine 0 degree. 1 kan? Ada yang jawab? 1. Okay, so meaning that D and Q, if the degree is kosong, the maximum value is 1 kan? So that's why you take the highest one here. The highest value that you can get for the ranking is 1. If in the calculation you compute 1.1 or 1.5, that means something wrong with your calculation. It should not be more than 1. Okay, so that's why they say the formula is looking at the degree of similarity. Okay, so they use the cosine theta. So if the theta is 0, your value is 1. Okay, and this is the calculation lah. Okay, okay. So the advantage of using the vector model is that you now will be able to perform the ranking using the cosine ranking, and also for the long document, you can normalize your document using the document length. Okay, but the only disadvantages is that your term document matrix, you only capture a single index. So you need to perform term-term correlation if you want to find out that correlation between two terms. Okay, so this is your uh, first journey into the text modeling. How do you model the text? How do you represent the text using the model that we have? And then how do we use the cosine function in order to in order to quantify the similarity of the document? Okay. Any question? If you okay, can you type number 777 three times? Wah, siapa yang cepat sekali? Yang first sekali. Turai. Siapa yang last sekali? Last sekali dia. Oke, yang last sekali tidak apa, yang langsung tidak respon yang bahaya. Okay, so that's it for today. I will see you tomorrow for the tutorial. See you tomorrow. Thank you for your time.
Okay, thank you, Dokter.
Welcome.
Thank you, Doctor.
Welcome.